In a regression analysis, when we regress y on x, we believe that x can help explain part of the behavior, or if you like, part of the variation in y. It is in fact based on that expectation that we conduct a regression analysis by hypothesizing that this parameter right here, b1, is not equal to 0 because it measures the strength of the relationship, or the existence of a relationship actually between y and x. So that if a relationship does in fact exist, then we know that we can say something about y given the values of x. A variable is called by that name variable because it changes. Its values may vary, that is, may change over time or cross-sectionally. In the circumstance, we hope that its relationship, that variable's relationship with x, can provide a path to find answers as to why it changes. So pursuant to that, I show here that the total variation in y can be broken down into two parts: explained variation and unexplained variation. Explained variation would be that portion of the total variation of y that is explained by its relationship with x. And then unexplained variation will be captured by, if I go back here, this error term over there. So I show it in a clear, using clear mathematical symbols here. Total variation is captured as the difference between the values of y and the mean of y. Now remember that in basic statistics, when you calculated the sample variance, we showed that to be the total difference between the values of y and its mean. So this is total variation right here. And then when you divide that total variation by the degrees of freedom, you call it variance. So this is the numerator of that total variation expression, the numerator of the variance. And this is shown to be equal to explained variation, which here is the difference between y hat and y bar, where y hat is actually the trend line, the regression line, as I explained right here, the predicted value of y. And of course, y bar is the mean of y. And then the unexplained variation would be the difference between the values of y and the trend line, the regression line. So more formally, this explained variation is calculated as sum of squares total, meaning, take this total variation, square them and sum them up. And similarly, the explained variation is calculated as sum of squares regression because, again, it is the portion of the variation that is being explained by the regression of y on x. And then finally, unexplained variation is calculated as sum of squares error, which is the difference between the square difference between the values of y and the regression line. So this is how that looks. All right, using this sample data right here between x and y, I construct the scatter plot and then show the regression line, which is this line right here. So this regression line is our y hat. And then consider a particular observation right here labeled as y sub I, which is an observation, one of the observations of the variable y. Now look at the difference between where this observation lies and the mean, which is this red line here, the mean of the data set right here, this y values. The mean is 654. So I've represented that using this red line. The difference between this point and the red line is our total variation. So that's y minus y bar, the mean. That's what you see right here. Now though, of this total variation, this portion between the regression line and the mean is your explained variation. See, the regression line is y hat and the mean is y bar. And then this residual right here, which is actually marking the error component of the total variation, is your y minus the value of y minus y hat, the regression line. So this is the unexplained component of this total variation. Now, obviously, as you would imagine, if x is an important variable in the regression model, then the proportion of the variation of the total variation in y that would be explained on account of the regression would be quite high. So now, in that sense, let's formalize the calculations of the explained and unexplained variation. The measure of explained variation is also referred to as the measure of goodness of fit and is called the coefficient of determination, r square, which actually this is the square of the correlation coefficient. So if you have the correlation coefficient and you square it, in the case of a simple linear regression, that's going to give you the coefficient of determination, our measure of goodness of fit that measures the proportion of the total variation in y that has been explained by the regression, and is calculated as the ratio of explained variation to the total variation, where explained variation is the sum of squares regression, which I showed you earlier, and total variation is the sum of squares total, which also you saw earlier. Now, you can also calculate this alternatively as 1 minus the proportion of the total variation that's unexplained, which is sum of squares error divided by sum of squares total. If you subtract it from 1, that's going to give you the same thing as you would get if you were to divide sum of squares regression by the sum of squares total. So if all of y has been explained by x, then r squared should be 1, which is 100%. If none is explained, it will be 0. So the value of r squared ranges between 0 to 1. For unexplained variation, there are two quick measures we can use. One is the mean square error, which is really the sum of squares error. We divide that by the degrees of freedom, which is n minus k, where k, as I note here, is always going to be equal to 2 in a case of a simple linear regression, because there's just going to be two parameters being estimated using b0 and b1. So 2 parameter estimates. So n is the sample size. And the other is simply the standard error of the estimate. The standard error of the estimate is the square root of the mean square error. So you can view this, the mean square error, as your measure of unexplained variation, or the square root thereof, which is the standard error of the estimate. So really, some refer to the mean square error as the variance of the regression model. Let's see how that works using our simple data set, which earlier we showed that the slope estimate is 0.7 and the intercept parameter estimate is negative 0.10. So with that, let's calculate sum of squares regression and mean square regression, measures of unexplained variation in addition to r squared, which is the most succinct measure of explained variation since it's bounded between 0 and 1. But again, remember, to calculate r squared, we need to have sum of squares regression and sum of squares total. I go back here. To calculate r squared, we need to have sum of squares regression and sum of squares total. These are measures of explained variation, providing us with this more succinct measure of explained variation. So let's go forward again. So now y hat is the regression line, which is defined as such. b sub 0 is negative 0.10, b1 is 0.7, and then for each value of x shown right here, we calculate out the values of y hat. And that's what you see right here. The calculations are shown here. And then also for y bar, which is the sample mean of y, we find it to be 2, which is the sum of these divided by 5. It's going to be 2. And then we want to get y hat minus y bar. So this 0.6 minus 2, square it, you get 1.96. This 1.3 minus 2, which is this 2 here, squared, would give you 0.49, and the beat goes on, and you get all these values, and then you sum them. And this 4.9, that is your SSR, your sum of squares regression, divided by the degrees of freedom, k minus 1. For the mean square regression, k is 2 always, which is same thing as 1. So 1 divided into 4.9 is 4.9. So in a simple linear regression, you're going to find that sum of squares regression and mean square regression are going to be identical for the most part. And then to calculate the coefficient of determination, we're going to divide sum of squares regression, which is our 4.9, by sum of squares total, which, remember, sum of squares total is y minus y bar. So for each value of y shown here, we subtract the mean of y shown here. Squaring the differences will produce these results, which when added together would give us 6. And that's the 6 you see here. Divided into the sum of squares regression, we get 0.82. So as you can see, since the value of r square ranges between 0 and 1, a value of 0.82 is pretty high. Caution though, r square is a descriptive statistic. In other words, it simply describes, in this case, the proportion of the variation in y that has been explained by x. Specifically, r square of 0.82 means that about 82% of variation in y has been explained by the regression. Pretty high. And then to calculate the sum of squares error, mean square error, and standard error of the estimate, we do the following. Remember, sum of squares error is y minus y hat. We already have our y hat calculated earlier. These are the values right here. And we subtract the values of y hat from the various values of y right here. So these are the results. And this difference, remember, is error. So squaring them, we get these values. Adding them, we get 1.1, and that's what you see here. Divide 1.1 by the degrees of freedom, we get mean square error, which degrees of freedom is 5 minus 2 because n is 5 and k is always 2 in this case. So this is 3 divided into 1.1, you get 0.3667. And then when you take the square root of that, as I show here, that's your standard error of the estimate. And that's it as far as the measures of variation are concerned in the context of a regression analysis.